In this video, we are going to be talking about calculation of equilibrium concentration, and this is one of the applications of the equilibrium constant. So instead of talking about, okay, this is step 1, this is step 2, 3, 4, and so on, I decided that we will discuss the example problem as we talk about the calculation of the equilibrium concentration. And I've picked problem number 7.9, and maybe in the next video we can discuss 7.8, and I will do it in relation to these steps. Okay, so first of all, let's look at the question. 3.00 moles of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin. Calculate the composition of the mixture at equilibrium, that is Kc equals to 1.80. So let's quickly write down what is given to us. So we've been given that Kc. So for this, let's also parallelly talk about the various steps given in your textbook. So in case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations, the following steps will be followed. So first, let's write down Kc equals to 1.80. Now, here we've been given PCl5. PCl5 is kept in a closed reaction vessel, right? And so initially, so we need to write the balanced equation. So PCl5, and I know it might feel like, oh, how do I write the balanced chemical equation? Most of these reactions should be something you're familiar with. So PCl5 is an equilibrium with PCl3 plus Cl2. Now, this is the balanced chemical equation. 3 plus 2 equals to 5, and P, just one phosphorus atom. Now, under the balanced reaction, make the table that lists for each substance involved in the reaction. So we need the initial concentration. So initially, our initial concentration is going to be 3.00 for PCl5. It's going to be 0 for PCl3 and another 0 for Cl2. Okay, now the next one we need to write in this table is we need to talk about the change in concentration on going to equilibrium. Now, let's assume that X moles of PCl5, okay, are dissociated. So X moles of PCl5 is getting dissociated. So this is the change in the concentration, right? The next one is the equilibrium concentration. So equilibrium, when it's at equilibrium, our concentration of PCl5 becomes 3.00 minus X. Concentration of PCl3 will be X. Concentration of Cl2 will be, again, X. Now, if for some reason, let's assume our chemical reaction had 2 PCl3, this is again a very hypothetical one, then you would say 2X. It depends. You will add the stoichiometric coefficient in the front of the one that we assume. So here, however, it's just going to, since they are all just one, PCl3 and one Cl2, it's going to be X and X. So in constructing the table, define X as the concentration moles per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. And that is what we did just now. Now, the next one is going to be step 3. Now, here we've been given the value of Kc. Now, obviously, we are going to be calculating Kc for this equation. So, Kc for this equation will be equal to concentration of PCl3 into concentration of Cl2 divided by the concentration of PCl5. And remember, 3.00 moles is the initial concentration. So, next thing is we'll be substituting the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. So let's substitute it. Now we know Kc, actually, let me just get to the next line. Okay. Now we know the value of Kc is 1.80, right? So I'm just going to make that note here. So we know Kc equals to 1.80. So 1.80 equals to, right, the concentration of PCl3 in equilibrium, which is X into X divided by 3.00, actually 3.00 minus X. Okay, now this in turn is going to give us a quadratic equation. If this was actually one of the, I think, yes, the quadratic equations, I did use a calculator to confirm if I did it the right way. 3.0, actually, you don't have to write 3.00, we can just say 3. So 3 minus x equals to x squared. Now, this, when we simplify, we get the equation x squared minus, no, actually plus, because we are moving it around like this. Like when we move this to this side, the sign changes. I'm sure you learned all of this in math. 1.8x plus, actually, there's a minus here, minus 5.4. Now, this is the quadratic equation. Now, we know for the solution of x, x equals to minus b plus minus root over b squared minus 4ac divided by 2a. Now, here a equals to 1, b equals to 1.8, and c equals to minus 5.4, because we need to take our the sign in front of each of these digits along with the I think I forgot what they're called, but we need to take the sign with it. So x equals to, so we get x equals to minus b, which is minus 1.8, plus or minus root over 1.8 square minus 4 into a, that is 1, into minus 5.4 divided by 2 into 1. Okay, now this is equal to minus 1.8 plus or minus root over 3.24 plus 21.6. And yes, I pre-solved this problem. 2.6 divided by 2. When you simplify this, you get minus 1.8 plus or minus root over 24.84 divided by 2. Now, root over 24.84, I'm pretty sure you know how to get the square root out. So minus 1.8 plus or minus 4.98 divided by 2. Now, there are two ways you can go about this. You can either have both as minus, and if it is minus, our concentration would be negative. And usually concentrations tend to be a positive value, so the minus value is going to be out. So we will solve the equation for x with just the positive sign. So minus 1.8 plus 4.98 divided by 2. And this is equal to 3.18 by 2. That is equal to 1.59. So this is the next step, that was substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for x. If you are to solve the quadratic equation, choose the mathematical solution that makes chemical sense. In this case, the one that made chemical sense was for us to have a concentration value which was positive, and because of that, we did not consider the negative 1. The next one is step 4. Calculate the equilibrium concentrations from the calculated value of x. So we will be doing that next. So, oh, actually, let me just scroll up. So from all of this, we know x equals to 1.59. Okay, so from the beginning, so concentration of PCl5 equals to 3.00 minus x, which is 3.00 minus 1.59. So that is equal to 1.41. Concentration of Cl2 equals to concentration of PCl3, which is equal to value of x, which is 1.59. And if you want, you can actually cross-check. And if we have done this problem correctly, we should get that the value is equal to the value of Kc. So basically what you will do is Kc will be equal to concentration of PCl3, that is 1.59 into 1.59 divided by 1.41. So 1.59 plus into 1.59 divided by 1.41. Let me, yeah. So 1.59 into 1.59 is coming about 2.52 divided by 1.41, which I hope is equal to 1.80, which is 1.78. And if you want, actually, let's do it this way. So 2.528 is the value for the numerator, which can be taken as 2.53. And then if you divide it by 1.41, you get about 1.79, which is equal to 1.80 by rounding it to significant figures. Actually, 1.8, more like. Point is, it's approximately equal to the original value of Kc. So with that, we're done with the calculation of the equilibrium concentration using the equilibrium constant. So basically, we started with writing the balanced equation, and then we used the initial concentration and the change in concentration, and then we talked about how it is in equilibrium, and then we substituted and got the quadratic equation for the value of x and solved for x. And then we got the concentrations of the reactants and the products. In the next video, we'll actually be discussing question number 7.8. This is another example problem. But in that case, it's more about the partial pressure and not the concentration. And that's why I wanted to use this to get the equilibrium concentration part of the topic done. I hope you understood this. In the next video, we'll be discussing question number 7.8.